Hey everybody, welcome back. Welcome to the second video for this part of part 3. So in the last video we introduced the laws of reflection and refraction. And what I want to do here, continuing with these PowerPoint slides, is look at a special case of reflection called total internal reflection, or TIR. Okay, so I remind you of Snell's law. You see it written up here. And what you see down here are just some rays that are in the bottom blue material with index N1. And these rays some of them are actually getting transmitted into the upper material N2. Now we're going to look at the case where N2 is less than N1, because that's one of the conditions that are required for light to undergo TIR. So the light is in a higher index material and trying to enter into a lower index material. So maybe from glass into air, as maybe indicated in this picture. Okay, so if you look at ray 1, the ray is going straight up in this material with index N1. Now, if I were to draw the surface normal for that ray, it would also be a vertical line. Right? In fact, here's a surface normal drawn for ray 2. So all the surface normals for these rays would be these dashed vertical lines. Well, for ray 1, that means the angle of incidence is 0. Right? The 0 angle means the ray is right along the normal line. The sign of 0 is 0. So the only way you can satisfy Snell's law, the law of refraction, is if theta 2 is 0. And that's what you see right here for ray 1. The transmitted angle is also 0, so the transmitted ray goes right along the same direction. This is known as normal incidence. The ray is normal or perpendicular to the interface, and that's the only time that the transmitted ray doesn't get bent. So it's actually not a true statement to say that light always gets bent when it enters a different material. If the angle of incidence is 0, i.e. normal incidence, the transmitted ray does not get bent. But any other angle of incidence, it will. So that's shown in ray 1. So here's a case where in ray 2, where the light does get bent. And because the light's going from high index into low index material, you can see that the light does get bent away from the surface normal. In this picture, theta 2 is bigger than theta 1. And I do want to criticize this picture that I admit I borrowed from a source, but you can see their surface normal, their dashed line? See how it should be moved over just a smidgen to the right so it intersects those two rays. But they almost got it right. But this angle, this tiny little angle here, theta 1, is less than theta 2. Now, if you increase the angle of incidence, and that's shown in ray 3, the light gets bent with an even larger angle away from the surface normal. In fact, let me see if I can do this. I may not be able to because my PowerPoint skills are somewhat lacking. But I think, yeah, let me see. Let me draw the surface normal. There, that's not too bad for ray 3. So for ray 3, this angle is the angle of incidence, and you get a larger theta 2. But that theta 2 is even larger than for ray 2. So as you increase the angle of incidence, the light gets bent further and further away from the respective normal line. But an interesting thing happens, and that's shown in ray 4 here. You'll get to a point where this angle theta 1 is at a certain value where Snell's law says that theta 2 is 90 degrees, which means that the transmitted ray goes right along the interface, and that's shown in ray 4. For ray 4, if I were to draw the surface normal, it would look like that. See, this angle right here, theta 2 for ray 4 is predicted to be 90 degrees. Now, that angle right there that angle of incidence for ray 4, it predicts 90 degrees for theta 2. That's going to be a special angle for this interface, and it's known as the critical angle. So when theta 1 is equal to this special angle, we call it theta c, then theta 2 is predicted to be 90 degrees, and that's called the critical angle. I'll summarize that in just a second when I click this. But the interesting question is, what if the angle of incidence, so what happens if theta 1 is bigger than this critical angle? Okay, now if you go up to Snell's law, the law of refraction, it predicts that the sine of theta 2 has to be greater than 1. And if you remember some trig, right, that's impossible. So Snell's law actually breaks down if the angle of incidence is greater than the critical angle. Well, what happens physically? It turns out that there is no transmitted ray. Snell's law breaks down because there is no transmitted ray, which means all of the light has to be reflected, right? Remember, when the light hits that interface, some of the energy is being reflected, some is being transmitted. Now, in this picture, for rays 1, 2, 3, and 4, they're not showing the reflected rays, okay? But there is energy being reflected. But if the angle of incidence is greater than the critical angle, all of the light energy is reflected. And that's indicated in ray 5. See, if I were to draw the surface normal for ray 5, it would look like that. This angle right here is bigger than the critical angle, which means all of the energy is reflected, as indicated in that reflected ray. And the angle of reflection will equal the angle of incidence for ray 5, but all the energy is reflected. In fact, what you observe is that as you go from ray 1, normal incidence, to ray 5, more and more of the energy is getting reflected. So as that incident angle gets bigger and bigger, more energy is being reflected and less is being transmitted. And once you're beyond the critical angle, all the energy, all the light is reflected. So that's known as the law of, known as total internal reflection. Okay, so this picture just shows you at the critical angle, the transmitted light is refracted at 90 degrees. Okay, that's what that picture shows you. Now, let me get rid of the sketches there. Erase all ink on slide. Yeah, that way you can see. This is important. So for TIR, total internal reflection, to occur, two things have to be true. N1's got to be bigger than N2, so the light has to be going from a higher index material trying to go into a lower index material. And then the other thing that's required is that the angle of incidence is greater than the critical angle. Now, you can actually find the critical angle for an interface. The way you do that is you use Snell's law. So if theta 1 is the critical angle, theta c, theta 2 by definition is 90 degrees. Well, it turns out that the sine of 90 degrees is 1. So that means the sine of theta critical has to be n2 over n1 if you just solve this formula for sine of theta critical. So what you can do is, on your calculator, you can take the inverse sine, sometimes called the arc sine, of n2 over n1, and that will give you the angle. Okay, it's a function on your calculator, and you might recall from trig that to find the angle of a trig function, you take the inverse trig function. Okay, so that is the critical angle and TIR. Okay, so here on this slide, I'm just summarizing again the two conditions that are required for TIR. Okay, and then I just calculated the critical angle for some typical interfaces. So for instance, if a light ray is in water with an index of 1.33 and trying to enter air with an index of 1, remember for air we just take the index to be 1, it turns out that the inverse sine of 1 over 1.33 is 48.8 degrees. So that would be the critical angle. If the light ray is in glass with an index of 1.5, trying to enter air, the critical angle is around 42 degrees. And glass to water, indices 1.5, 1.33, about 62.5 degrees. So again, if you have, let's say like in an aquarium, right? There you might have a light ray in glass trying to enter water. For this particular interface, if the light ray comes in at an angle greater than 62.5 degrees, all of the light will be reflected back into the glass. None will enter the water. Okay, so pretty neat. Okay, now I do want to show you a demonstration video, and what I'm going to do with these demonstration videos is, instead of putting them into the PowerPoint that you guys can download, because that would make them really big, and also there's no audio on the demonstration video, so if you ran it, you would just see a picture with no audio. I'm going to run these in a separate PowerPoint that I'm not going to post. So if you want to watch the demonstration videos, you're going to have to watch the lecture videos. But this is just a reminder for me to run this demonstration video. So let me go ahead and just end this show and go to just have another PowerPoint where we have the video. Okay, so let me go full screen. Now, this is right now, this just shows a rectangular piece of plastic, okay? And I'm going to be shining a laser beam through this. This piece of plastic, when it was made, they put some small particles in with the plastic. So when the laser beam goes into the plastic, it actually reflects off of those tiny particles. So you can actually see the laser beam traveling in the plastic. And again, this is in low light level, so that's why it's a little bit granular, grainy, because I want you to be able to see the laser beam. Okay, so let me see. Let me just run it. Okay, so here what you see me doing is bringing in a piece of plastic. I'm going to pause it. So this is just the fact that this is a triangle isn't important. I just need another block of plastic. And I'm setting this so that there is an air gap between these two pieces of plastic. So if light is going to go enter the triangle from the rectangle, it has to go through some air. That's important. So that's all I'm doing here. And then I'm going to take a red laser pointer and I'm going to enter the bottom of this rectangle. Okay, right there. Let me just pause this. Okay, guys, sorry for the interruption. I was having issues. Well, it's really me, but getting my stylus to do what I wanted it to do in full screen mode. But okay, we're back. So what we have is the laser beam is entering the bottom. You don't see it, but it's traveling in the air. And I'll highlight it for you. So it's like this. The laser beam is coming in like this. And from the air, and here's the first surface normal. So it's going to get bent towards the surface normal, right? So that's what you see with this red line, this red laser beam right here. See, this angle right there is smaller than this angle. Then the light hits the plastic air interface. Remember, there's an air gap between the rectangle and the prism. So if I were to draw that surface normal, it would look like this. This ray, you don't see it in the air because there's nothing to scatter or reflect off of, but it's going like this. Okay, whoops. This ray right here. Okay, sorry for that one going to the left. But see, that's definitely bending away from the surface normal as it enters the air. Then it's entering the triangular piece of glass, and that surface normal would be like this. So this angle right here is smaller than this angle. So the light ray is getting bent towards the surface normal. And then over here now, this is not a horizontal interface for that top of the triangle there on the right. It's slanted. So the surface normal would be like this, like that. Okay, perpendicular to that slanted side. And you can see that here's the angle of incidence for the ray in the triangle piece of plastic. Here is the transmitted angle, and that's bigger. So the light is bending away from the surface normal when it goes into the air. Okay, so we can see the law of refraction working. And I also want to point out that we definitely have light going across the air gap and then entering the triangle, right, piece of plastic, the triangular piece of plastic, and then entering the air above that. Okay? Now, the angle that I'm going to focus on is right back here again, this angle right here, because the light is in plastic, right, and it's trying to enter air. Well, that angle right there, that angle of incidence, is less than the critical angle for, that's a theta sub c, it's less than the critical angle for the air plastic. Right, so this horizontal interface, that's the interface between the plastic and the air. There's a critical angle for that interface, and this angle for this particular ray, red ray in the square plastic or rectangular plastic, is less than the critical angle, which means that some energy is actually making it into the air and then into the triangle. Now, what you can't see very well, it's there, but it's really faint, is that some energy is reflecting off of that interface and coming back through the rectangular plastic, okay? And some of that energy is actually transmitting away from that surface normal this way. And you can see some of that energy is hitting the table and reflecting, and you can see that right there, okay? But again, the main thing I want to show you is that there is light that enters from the rectangular plastic block into the air, and you can see that because it goes into the triangular piece of plastic. Okay, so now let me clear all these, and we're going to let the video go, and I'm going to come in with a different angle of incidence for that plastic air interface, and TIR will occur right before your eyes. Oh, and there it is. Oh, my laser beam went off. Okay, I'm going to pause it. Okay, because now here's what's happening. Okay, so I have to come in from the side in order for this to happen. So it's sort of hard to see. In fact, right there, that's the end of the laser. Again, so the light's coming in like this. This is the surface normal for that first interface, and it's coming in like this. So this is the angle of incidence for that vertical interface, and the light is bending towards the normal. Okay, so that would be the refracted angle. But this is what I want you to look at. Look, you don't see any laser energy in the triangular top piece. So the light that's coming this way is totally internally reflecting off of that plastic air interface. Because if I were to draw the surface normal, here it is. This is the angle of incidence for that particular laser beam in the plastic. That's bigger than the critical angle. So that angle right there is bigger than the critical angle for the plastic air interface. So all of the laser energy is reflecting back into the rectangular plastic block. That is amazing. So that's TIR in occurring, well, I was going to say real time, I guess recorded real time, okay? And then you can't see it, but there is light. So when this laser beam hits right here, there is some light that refracts into the air, and it gets bent away from the surface normal, so it's going to be bending like that. And some energy is actually reflected. Again, it's very faint, so you can't see it, back into the plastic. Okay, but the main thing, again, I want you to see is that TIR is occurring right there. Okay, that's it. I'm going to end this video, and we're going to do an exercise in the next video. Okay, bye.